Okay, perfect. Thank you, everyone. So now our last talk of the night. Hello. Thank you. So our last talk of the night, Roman from Dragonfly.
Yeah. Very excited to be here. I was told that there are 130 attendees here tonight. Quite a lot. And I don't know, it may sound counterintuitive, but I would like to make the following claim. There are 3 people here tonight that share the same birthday. Again, with 130 people, 365 days a year, it's what, less than half birthdays each day on average. And yet, with a high probability, my claim is correct. And I don't know if you heard about this, but it's known as a birthday paradox, right? And this phenomenon is kind of related to my talk today about scaling workloads on the cloud, in the cloud, sorry. And yeah, I'm Roman, and I work at Dragonfly DB, where we develop an in-memory data store called Dragonfly. And Dragonfly is compatible with Redis. I hope you all heard about Redis, Valky now. And it's compatible, and this compatibility ensures that it provides the same atomicity guarantees like Redis, but it's much more efficient due to its multi-threading capabilities. Basically, it can scale vertically. Okay. You're of course welcome to check it out. It's hosted on GitHub. It's source available. Has lots of stars. Lots of people are already using it. We launched it more than 2 years ago. Okay, so we are going to talk about scaling workloads, and just to cover our basics, I'm sure you all know this. Horizontal scaling is when we use multiple nodes to handle our load, and vertical scaling when you use bigger, beefier machines with more CPU and memory, right? And stateful workloads, stateful sets, stateful pods, are those that have a unique state attached to them, a sticky identity, and they are not interchangeable. Usually the state is either in memory state or on disk. A database, for example, could be a stateful workload. And usually if one of the pods in the service fails, the whole service is considered to be unavailable. You need all the data for this of the service because data is distributed there and it's important. It's part of the state, right? Cool. All right, so we are all accustomed running our applications as horizontally scalable layers, right? With stateless apps. But today I would like to talk about weaknesses of horizontal scaling when we manage or run stateful apps. And we'll also talk about why those weaknesses do not manifest themselves with stateless apps. So again, the focus is on horizontal scaling and stateful apps in this talk. And we are going to cover possible quirks of the incoming traffic that hits our service. We'll talk about constraints of the cloud that can affect our pods, the performance of our pods, our instances. And we'll also talk about how cluster size affects its availability or resilience. Okay? 3 main points. And we'll start with the properties of traffic. And for that, we're going to play a little game. We're gonna throw balls into bins. And thanks ChatGPT for this picture. Yeah, and for that we are going to use this simple function. It's 4 lines long function that simulates throwing n balls into k bins. For each ball, we randomly choose a bin and we add the ball into it. And then we look at the distribution of balls across bins. And here we see an example run of 300 balls being thrown into 10 bins, and on average it would be 30 balls per bin, but you can see that like some bins are smaller, some are bigger. It reaches, in this specific scenario, 36 balls for one of the bins, meaning the ratio between the biggest bin and the average is 1.2, okay? And if we repeat the same simulation, but now with 20 bins, okay, same 300 balls, we'll see that the volatility of the load increases. The average is now obviously 15, right? But the biggest bin is around 21, 22. We have the ratio of the biggest bin to average is almost 1.5, right? And why it is important for us? So let's suppose we need to buy those bins. We want to contain all the balls, okay? So in theory here, we would need, like the best case scenario would be to buy bins of exactly size 15 in order to cover 300 balls, 20 bins of size 15, but obviously it's not possible. So we need to buy bins of size 22. By the way, those simulation runs will, of course, change from specific run. It's random, of course, but it's going to be around 21, 22, maybe 25, maybe a bit less than 20. But in general, it's going to be much higher than 15. So if we talk about provisioning, we're slowly starting to use DevOps words. If we talk about provisioning of those bins, we need to over-provision our capacity in order to contain all the balls. And with more bins, our traffic volatility increases. So we need to use bigger margins in order to hold all the balls, to catch all the balls, otherwise they will be overflown. And this actually can be proved by math. And that's like the key statement that I would like you to kind of remember. For the same load, if we increase number of bins, the volatility of traffic increases. Okay, that's the key point. Now let's apply this to real-world scenarios. So let's replace bins with load balancing servers and our balls with TCP connections. And let's suppose that our service handles lots of TCP connections, but only a handful of them are heavy hitters, meaning they inflict a substantial amount of traffic on our nodes, okay? Could be dozens or hundreds of connections, but they're like very important ones. They inflict lots of traffic, inflict lots of load on our servers. Then we can apply the same model like before, and we'll see that those TCP connections are distributed unevenly on our nodes, and some nodes will be loaded more than others, okay? And the same kind of rule applies. If you use more nodes, the volatility of lack of balance will increases. Now with TCP connections and load balancing service, it's not a serious problem because this is a stateless service. So TCP connections can disconnect and reconnect to other service, and the service will gradually balance itself. So there are other like examples when we are behind load balancers, and there are like routing policies that can help. But in general, it's stateless service, and that's why kind of this lack of balance is not critical to our service. But let's apply now this to a stateful scenario. And here I took as an example a Boolean queue framework running over a Redis cluster. For example, Boolean queue is a very popular job management framework among Node developers, but there are others like Laravel for PHP and Psychic for Ruby and others in other languages. And they use a Redis cluster to manage and store job queues on the cluster, right? And here, again, let's say we manage dozens or hundreds of queues. Each one of the queues can inflict a substantial amount of traffic on hitting our Redis shards. But those queues are distributed randomly across multiple shards, but this randomness doesn't mean that it's uniformly spread. So we have this lack of balance between queues, and we'll see how our Redis shards, some of them are loaded much more than others, and this lack of balance will be consistent with time. Okay. By the way, this example can be applied also for other use cases. It doesn't have to be job management queues. It can be any other entities that is relevant to your application use case. The main thing that it inflicts substantial amount of traffic on your service, and so for this model to work. Okay, so just to recap what you saw so far. If we have a cluster, the larger the cluster is, the more volatile the traffic can be. With stateful services, we have a harder time to to manage or to move or to mitigate the problem of lack of balance, because the data is persistent. We need to actually migrate data from node to node in order to fix this. And with bigger clusters, for the same load, we'll need to over-provision higher margins in order to cope with our load. In other words, for larger clusters, we waste more resources. I don't know if you knew about this. It was unexpected and counterintuitive for me when I first learned about this effect. But for the same load, the size or the horizontal dimension of the cluster can really affect how much we need to over-provision it. By the way, this model also explains the birthday paradox, and this example that I gave before about people having the same birthday here. Okay, so we covered properties of traffic, and now we'll talk about cloud-specific constraints. And for that, we are going to compare a networking spec on AWS. We are here in the AWS office. It's undoubtedly the most sophisticated and mature cloud out there, and yet, of course, it has constraints. Here, these constraints are related to multi-tenancy nature of the cloud. If you can see, the only difference between M5 large and M5 8 extra large is up to a word when we talk about bandwidth. And this may seem like a minor difference, but if you read the fine print, and by the way, it's pretty hard to find this documentation for some reason on AWS, but if you read the fine print, you'll see that the base or guaranteed bandwidth of M5 large is only 0.75 gigabits per second. In other words, it's 14 times less than the up to peak bandwidth that you get, which means we get very volatile performance, especially if we are like bottleneck on networking, for our smaller instances. So the smaller instance is, the more volatile performance will be, and this gonna decrease with the size of the instance. It's usually disappears, this volatility disappears around 8x large instances that are pretty big. Now, just to demonstrate how it looks like for a practical example, we conducted the following experiment. We reserved a dedicated host with 96 CPUs, and M5 metal. And it has 96 CPUs, and we launched there a single VM with 2 CPUs, and we ran a Redis process there, and we benchmarked it, okay? And we clocked 150,000 requests per second, okay? Now, if you extrapolate this to the rest of the host, right, it has capacity for 84 VMs of such size. You would get over 7 million requests per second maximum throughput rate. But then we just did that. We launched 48 VMs, and we launched a Redis cluster on these VMs, 48 shards, and we benchmarked this cluster, and it could only reach a bit less than 900,000 requests per second. It was 8 times less than the extrapolated number. What it means is that when we use like smaller instances, like M5 large, M5 like large instances, extra large instances, your performance can go down significantly without you understanding why, just because there is some other tenant on this host that takes your like resources. Okay. That's widely known as a noisy neighbor effect, and unfortunately there is not much we can do about this. It's kind of part of the multi-tenancy nature of the cloud, any cloud. Cool, so let's recap everything together. Sorry. Load distribution can become volatile with larger clusters. Node performance can become more volatile with smaller instances. Now, running large clusters with small instances is the most unstable configuration, where you can basically have some production issues, random production issues, and it's harder to maintain consistent quality of service when you use such configuration with lots of nodes of small replicas. Cool. So I would like to discuss our final point about how cluster size affects its availability or resilience. So we all know that things can break, software can have bugs, hardware can malfunction, of course not on AWS, but on some other cloud. And basically your servers can fail, right? And for teams that manage just a few servers, it's not a real problem. It's kind of the risk is negligible. Also for teams that run stateless apps, it's not really a serious issue because, well, a pod dies, then there are others that take its place, and just the traffic will be distributed among other pods. But if you remember, we talked about how with stateful services, every pod has its own unique identity, its own unique state. They are not interchangeable, meaning for the stateful service to be available, you need all of the pods to be available. And this condition is kind of strong. And that means in math terms that the probability of the failure for the entire service grows linearly with number of replicas. So just to give you an example, if you run a service with 100 replicas, then the probability of it's a stateful service, the probability of the failure will be 100 times higher. And that this final point kinda intuitive, because if you think about any system that has lots of moving parts and you need all of them to work together, you kinda understand that this system will be more fragile just because it has more moving parts, and if you have less moving parts, it will be less fragile. Okay, so I know that I talked a lot about horizontal scaling and its weaknesses with stateful apps. Please do not read it as if I was like saying that horizontal scaling is bad and vertical scaling is good. I didn't talk about vertical scaling because its weaknesses are apparent, right? You can't scale infinitely because you don't have infinitely big machines. Also, even like big machines, they have networking bandwidth constraints, etc., etc. So those limitations are apparent. Also, for folks that use, let's say, Python and Node, maybe they don't even have this ability to scale vertically just because those languages do not support multi-threading. So that's kind of also solves itself. But if you happen to run stateful services and you use either systems or languages that support multi-threading, I suggest, based on my personal experience, of course, to try first scaling vertically and then spread your load horizontally. That usually works better and has less reliability problems. Thank you. And we launched this year our cloud service, and you're, of course, welcome to try it out. And we have a special coupon here for you to try it for free. Thank you very much.
Thank you so much, Roman. Any questions? Here we go. Question over here.
Yeah. In the beginning, I think I'm trying to verify the assumption here. And the assumption is that the traffic is spread in a random manner. Does this behavior continue? Does this behavior happen also when you have like a more routed traffic, like a round-trip system or what?
Sorry, can you repeat?
I'm saying, based on your original assumption,
yeah,
which I believe, is that the traffic is randomly distributed among the nodes. So I'm asking that does this behavior where the volatility also occur when you have like a routed traffic, more routed traffic by the load balancer?
Oh.
Like let's say round-trip manner or what?
Yeah, it's a good question. So basically, what happens when you use load balancer and your system is behind load balancer, right? So basically, for stateless apps, so suppose your layer is stateless, then load balancer will probably reroute traffic based on some heuristic or strategy, like least smallest latency, least loaded. It really depends. So basically now we have this regulation of this actor that knows your system and plays along with it. In that case, of course, your traffic will be almost balanced because there is a regulator that kind of tries to rebalance the load. Okay? In my assumption, I assume that the entity that sends traffic is independent in a way. It's random, like when we throw balls, right? In that case, it can coordinate its behavior with the state of the system. Yeah.
Any other questions? Anyone? So, Andre?
Yeah, I mean, this chart shows basically the distribution if balls are of the same size. But what if balls are of different size and the size is random?
Well, it's also a good question. Usually in real-world scenarios, it's indeed what happens. There is like a power log distribution that people, applications store like blobs of, I don't know, 10 megabytes, and they're like hundreds of them, thousands of them, and then there are like millions of blobs smaller size and billions of blobs really small. So this is what usually happens in many scenarios. This only adds to lack of balance. It's just much harder for me to model, but if you look at the real use cases, that's exactly what happens. That this only increases the lack of balance that we can't like encounter for. And for stateless apps, unfortunately, once this huge blob is stored somewhere, it will consistently inflict this significant damage to, or load, sorry, not the damage, but load on that server.
Okay, last question. I think there was a question over here.
Yeah, I was interested in the last equation you showed. So basically,
Probability of a failure.
because
This one?
yeah, this one about availability. So if you increase the number of replicas, you would soon reach a state where the probability of server being available would drop to 0. So what would happen then?
In infinity, yes, but that's correct. Mathematically, you are correct, but you don't have, like, your basic probability of failure is 0. Very, very small. So probability of success, it's like 1 minus, right? So probability of success will be 0.999999, like, I don't know, 5 nines. And now if you use even thousands of shards,
It still doesn't matter.
it matters. It matters. Okay, I was working at Google. I was working at Amazon. It matters when you have huge clusters, but it's not 0. You can manage it.
Cool. So thank you very much again, Roman. Really, really appreciate it. Before we finish, this is the last thing between you.